Okay, folks, this is the introduction to terminal velocity. We're going to start with force diagrams. So let's get started. So the first thing I think might be important is to remember what we know about surface friction, and so we can see kind of what's the same and what's different. So the formula for friction is the fun formula, F equals mu times the normal. And I chose this diagram because, remember, this is what I call a suitcase problem. The normal force is not equal to the weight. It's a little bit less because the person is pulling a little bit upward, so they're kind of carrying some of the weight. But assuming that that angle stays constant, then the normal force is going to be constant. Assuming you don't change the surface type, then mu is generally constant. So the force of friction is a constant. So that means no matter where you draw this force diagram at point A or a little bit down the track at point B, the force diagram is going to look the same. Okay, so what that means is you can use the old school constant acceleration formulas, or what I'm calling physics Sudoku. All of those are legit. And if you want to define the work done by friction, since the force is constant, you can say FD cosine theta, where F is the force of friction, the distance is the distance from point A to B. Be careful, cosine theta is the angle between friction and the motion, which is 180, right? Because friction does negative work. Okay, so you could, given a distance, find how much energy friction had taken away and turned into heat. Okay, so, and it is opposite the motion, right? Because it's running in, the box is literally running into the nooks and crannies that are in front of it, underneath it. Okay, so that's surface friction. First of all, how do you recognize a terminal velocity problem? Don't assume that it says somebody jumps out of an airplane. Okay, that's not what determines whether what we're going to do for the next couple days is the right approach. This is what you want to do. You want to recognize that one of the forces, like surface friction, because it's going to slow you down, is a function of the velocity. So it's not constant because your velocity is generally changing. Okay, and you want to be careful. There's, first of all, the symbol for the force of colliding with the air molecules, which we'll talk about in a second. Sometimes it's R, some books call it a drag force. Either one is, I've seen both on AP problems. So the drag force is one of two things. It's some coefficient times the velocity, or it is some kind of coefficient, let me call that C, times the velocity squared. In general, I think this is true for really small things, and we're talking dust particles here, like not even like a feather, probably, like really small. And then this is what's true for large things. In general, you have both, but this term dominates at small particles going slowly, and this term dominates for large particles. Technically, you have both. Okay. But since we're learning physics for the first time, they're going to pick one or the other. Okay. If the problem says the force is BV, we're not doing that right now, but that turns into a differential equation, which you can solve. If the force is a function of the velocity squared, then the good news is you don't have to do differential equations because you can't solve that differential equation. Okay, I'm going to talk briefly about what B and C are. B is not a universal constant. B is it's called a drag coefficient, and it's kind of like mu, right? mu dependent on both surfaces. What are the nooks and crannies? How much are they interacting? This depends on the surface. So in the olden days, semi-trucks, the front of the truck looked like this, square and boxy, and then they realized, oh, I can make that more aerodynamic, and then you have those little things on the top of the truck. Okay, I got some pictures on the next slide. So B folds in a whole bunch of stuff, like how humid is the air, how dense is the air, how does the air flow around the object. So you will be given B, or you'll solve for B. So it's not a universal constant like 9.8. It is a function of the object that's going through the gas or air, as well as how dense the properties of the air. Okay, and then same thing for C. It's just telling you, hey, like how much air resistances are going to be. Okay, so moral of the story of this slide, force is a function of velocity, either V or V squared. So then I just found some diagrams just to convince you, that anything going through air, they study. How do I make the air flow around the skier better to reduce the drag? How do I make the air flow around the car better so that I have less drag? Okay, and clearly you can see the skier is crouching because why is it a function of velocity? The more air molecules you hit, more literally it is collisions, and you can model air resistance. You can derive that formula of F equals BV squared by literally saying, like I'm colliding with these air molecules. So you want to make yourself have as small a surface area as possible, but also let the air flow around you for other complicated reasons. Okay, so the faster you hit those air molecules, the greater the air resistance is going to be. Hopefully that makes sense, that the faster you go, the more air molecules per second you're going to hit, the greater the average force on you. Okay, and that's why you get better gas mileage at slower speeds. Okay, so hopefully now that you're kind of convinced about what air resistance is, how is that going to change my force diagram? Okay, so the good news is you're still going to use, we must never forget this. You're still going to have all those forces. Probably not going to have surface friction because you're going to, instead of surface friction, you're going to have air resistance. Okay, so you might consider this a type of F. You might also add another check mark. Anyway, you'll know it's a terminal velocity problem. What I'm trying to say here is, you're still going to draw the weight. You're still going to draw the normal force. You're still going to draw a rope if there's a rope. But similar to surface friction, you're going to think about which way is this object going, and that is not a force. So please don't draw it on the force diagram, draw it off to the side. And because you're running into air molecules by Newton's third law, they are hitting you back. And then this diagram called it a drag force. And this whatever it is falling through air molecules and hitting them, and it's got an upward force of drag or force of air resistance. Okay, so pretty straightforward. It's going to be opposite the velocity. Okay, opposite the velocity. All the other forces are going to be what you thought they were. We're not changing anything else. Okay. However, so finding the direction of the force, generally pretty easy, but it's not constant. That's why I wanted to start with the dude pulling the box. If you drop from rest for a split second, you haven't hit the air molecules. You're not hitting them at that instant. So for a split second, your acceleration is free fall. And we're going to see that again when we do the graphs together in class. Okay, so you just have the weight. And then you start to hit air molecules at a slow speed. And so they're going to hit you back with 300 newtons. But the weight is still bigger than the air resistance, so your acceleration is down, and your velocity is down. They both have the same sign, so you're speeding up. So now I'm hitting the air molecules at a greater rate, which is going to increase my air resistance term. But it's still less than my weight, so my acceleration is still down. So I'm still speeding up until at some point, so my air resistance increases until at some point you can see that it equals to the weight. So now those two forces are balanced and the person stops accelerating. Okay, so now my V is down, but my A is 0. So since I'm not speeding up, I'm not going to hit the air molecules any faster. So this is going to stay constant. This is caused by the Earth. That's constant. So I am never going to change that speed unless I change my shape, which will change that coefficient term that we were talking about, like opening a parachute. So that's why this is called terminal velocity, because you will have that velocity for the termination of your trip. Okay, so couple of things. You have seen something like this before. You saw that when we did the bungee jump problems, right? The weight was constant and the K delta X was increasing. And as long as mg was bigger than K delta X, you were speeding up. And then when it was equal, you stop speeding up, so your velocity is a maximum at that point. One of the challenge problems you're going to do is if you throw something up in the air, then your speed is up, then the air resistance is slowing you down and gravity is slowing you down. So clearly you're not going to reach a max speed. You're going to reach a speed of 0 as you turn around. Okay, so it's not, but this is more classic. Okay, if you wanted to find the acceleration at any given instant, you would say, up minus down divided by the mass. That's where these numbers are coming from. So you can see the person is speeding up because A and B are always in the same direction, but at a decreasing rate, right? I'm speeding up at 9.8. I'm speeding up at 6.5. I'm speeding up at 3.1. Oh, I'm not speeding up anymore. Okay, so there's a lot of hidden nuances. Just don't go on autopilot and go, my A is decreasing, therefore my speed is decreasing. Okay, so the force diagram is changing with time. So you cannot use the kinematic equations. You can't use physics Sudoku because acceleration is not constant. That's why we're doing it in this unit. Okay, 2 more slides. Hang in there. So this is what I call free points. The rest of the problem may be super complicated, but if they ask you for the terminal velocity of an object, what does that mean? Oh, that means my forces are balanced. Okay. And so the mass of the baseball and the drag. Oops. Yeah, sorry. I was typing this. So the drag force is 7.7 times 10 to the minus 4. I just made it V squared. There's some units in here to make this come out to be forces. So what would that be? Newtons per meters per second squared. Okay, so what is the terminal velocity? So easy question. You're going to set the forces equal. You're going to say, I know those forces are balanced. So 7.7 times 10 to the minus 4 V squared, which is positive because it's up, minus the weight equals 0. Okay, so we have the drag force, which was given, equals the weight. So then I calculated the weight was 1.46 newtons divided by 7.74, and then took the square root, and the terminal velocity of that baseball was 43.4 meters per second, which is about like 95 miles an hour. Okay, I tried to look up some real numbers. Okay, so really, really, really straightforward question. Terminal velocity means balanced forces, draw your force diagram, solve for what you don't know. Okay, so maybe you know the terminal velocity and you're looking for that B coefficient. Okay, super easy question. All right, moving on. The last slide. Finding the work done by air resistance. So that is also sometimes a classic problem. So this is a classic lab, which we may or may not do, where the coffee filter starts from rest at A, and then it lands with some speed at B, which you measure using a sonic range or a stopwatch or whatever. Okay, so you cannot say the work done equals FD cosine theta because the force isn't constant. Okay, you cannot say the integral work is the integral of F. You can say work is the integral of F dt, but what you know is the force is a function of velocity. So in order to integrate this, these two have to be the same variable, and they're not. Okay, so what you're going to do when you see that type of problem is say T me at A, changing height, plus the work done equals T me at B. Okay, and assuming your points A and B is, I drop from rest, so I only have MGH plus the work done, and I'm about to hit the ground. I'm going to call that sea level, equals 1/2 mv squared. That's how you're going to find the work done by air resistance. Okay, so again, it's not really a different problem than you've done before. You just don't want to get psyched out by the fact that there's going to be some new stuff, but you could have done this problem, you know, whatever, a month and a half ago. The only thing different might be they might, for some random reason, say, okay, I'm not going to go from A to B. I'm going to go from B to C, where at B, I'm already moving. Okay, and then you would have MGH because you're still not at sea level, plus you have some speed. Okay, but again, you guys can handle that. Plus work equals 1/2 mv squared at B. Okay, not hard. So don't, just because some things are different and a lot more complicated doesn't mean that some other things aren't exactly what we've done before. All right, that is it. Thank you for listening, and I'll see you in class.